let's discuss a very particular kind of tree, a very common kind of tree called a binary tree. So a binary tree is a special tree. It's a specific kind of tree defined by the fact that each node has at most two children. So that means every node in your tree can have 0 children, 1 child, or 2 children. So each node in the tree has a maximum of 2 children. Because of that, because that's the max number, the child nodes or the children are referred to as the left child and the right child. So again, binary tree, certain kind of tree, at most 2 children. So you can see this is an example of a binary tree. This node here has 2 children, 0, 0, 1, 2, 0, 0. So each node can have either 0, 1, or 2 children. So let's take a look at this example here. Is this a graph? It is. Is it a tree? It is. I don't see any cycles. Is it a binary tree? It's not a binary tree because this node here has 3 children. So if a node has more than 2 children, it's not a binary tree. It can be just a general tree, another kind of tree, but it's not a binary tree. For a binary tree, every single node in the tree has to have at most 2 children. So is this a graph? Yes. Is it a tree? No, because it has that cycle. And if it's not a tree, it can't be a specific kind of tree, so it's also not a binary tree. Is this a graph? Yes. Is it a tree? Yes, I don't see any cycles. Is it a binary tree? Again, no, because although this has 2 children, 0, 0, this one here has 3. So again, more than 2 children means that it is not a binary tree. About this one, so take a look. This is a graph, it is a tree, and it is a binary tree. So we have 2 children, 1, 2, 2 children, 1, 2, 0 children, 1 child, 1 child, 0 children, 0 children. Yes, all of the nodes have either 0, 1, or 2 children, so this is a binary tree. This one, it is a graph, it is a tree, there are no cycles, and it is a binary tree. This node has 2 children, 1 child, 0 children, 1 child, 0 children. So yes, that is a binary tree. This is sort of a classic example that you'll see of a binary tree. So this is a graph, this is a tree, and then again, this is a binary tree, 2 children, 2 children, 2 children, 0, 0, 0, 0 children. And this one, this doesn't look like your typical tree, but it is a tree, right? It's a graph, it is a tree, there's no cycles, and it's a binary tree. This node has 1 child, this node has 1 child, and this node has 0 children. So every node has 0, 1, or 2 children, meaning that this is a binary tree. This is a special kind of tree that's actually like a linked list, right? So this is a binary tree. You can also think about it as just a list, a linear list, because these are only just one-to-one connected. All of the nodes have exactly 1 child. So that's what a binary tree is. Now we can get a lot more specific about different types of binary trees. So a binary tree is a very general concept. It just means the only restriction on a binary tree is that it's a tree where every node has at most 2 children. So 0, 1, or 2 children. Let's learn about some more ways we can describe binary trees. So there's one way you can describe a binary tree by describing it as full. So there are actually 2 definitions of full. The first definition is that it's a binary tree such that every non-leaf has exactly 2 children and every leaf is on the same level. Okay, so that's one definition. An alternate definition is that every non-leaf has exactly 2 children. So it's essentially the same as the first definition, but it doesn't have the second part. So it allows leaves to be on any level. So for this alternate definition, in this one, every node has either 0 or 2 children. That's another way to say that. Okay, but there is no requirement that the leaves have to be on the same level. So this first definition is sort of more stringent, right? Both definitions say that every non-leaf has to have exactly 2 children. They're the same in that. So they both share that definition, that part of the definition. But the first definition is more stringent because it also says that every leaf has to be on the same level, and that's not part of that second definition. Okay, so because of that, because the first one is more stringent, if a tree is full using this definition, then it must also be full using this one. If a tree is full using this definition, it may or may not be full using the first one. Now, the first one is kind of more common. You'll see that one used more often. It's also the one used in our textbook, but you will also see this alternate definition used. So if you hear someone say, a full binary tree, you might need to clarify which definition of full are you using. Here is an example of a tree that is full by one definition, by the second, but not by the first. Okay, so this tree here, first of all, it is a binary tree, right? This node has two children, 0, 2, 0, 2, 0, 0. So it is a binary tree. Is it full using the first definition? Well, does every non-leaf have two children? Let's see, this is a non-leaf. It has two children. This is a leaf, so we don't care. This is a non-leaf. It has two children. This is a leaf. We don't care. Non-leaf has two children. This is a leaf. We don't care. This is a leaf. We don't care. So yes, that part is true. Every non-leaf has exactly two children. But is the second part of the first definition true? Is it true that every leaf is on the same level? Well, no, that's not true. Here's a leaf on this level. Here's a leaf on this level. Here's a leaf on this level. Here's a leaf on that same level. So using the first definition, no, this tree would not be full. But using the second definition, yes, this tree would be full, because the second definition only requires that first part, that every non-leaf has two children. So it is possible for a tree to be full based on the second definition, but not full based on the first definition. Now, in general, when I say full, I am referring to this first definition. That's the one that our textbook uses. That's the more common one, so I will be using that one. But both of them are correct, and in the slides here, I am going to show you, I'm going to use both of them so you kind of see the differences. Another way we can describe a binary tree is as whether or not it is complete. So a binary tree is complete if, again, every non-leaf has exactly two children. So that part sounds like full, except there's an exception here, except possibly on the second lowest level. So not the lowest level of the tree, but the one right above that. On that level, the nodes are allowed to only have one child. On the lowest level, the leaf nodes all have to be as far left as possible. Okay, so this is a bit of a more complex description here. So again, let's think about this. If we think at anywhere other than the second to lowest level, all of our other non-leaves have two children. On that second to lowest level, our nodes are allowed to have less than two children. But on that lowest level, the leaf nodes all have to be as far left as possible. Okay, so a complete tree, and we're going to look at examples of that in a minute. A complete tree may or may not be full. So just knowing that it's complete does not tell you whether or not it's full. If you have a full tree using that first definition, that tree will always also be complete. If you have a full tree using that second definition, then you can't tell. It might or might not be complete. Okay, so it gets a little complex thinking about full and complete, but I think the best way to do it, and this is what we're going to do in looking at some examples, is you just want to write down the characteristics that have to be true to meet that description, and then just look at your tree and evaluate it and see if it meets that definition or not. So let's look some examples. So I'm going to show you a tree, and I want you to pause the video, think about whether this is full using the first definition, full using the second definition, and complete. And then we're going to go over the answer. So take a look at this one. All right, so this definition is full by both, or this tree is full by both definitions and complete. So it is full because each non-leaf is full by the first because each non-leaf has two children. This is a non-leaf, two children, non-leaf, two children, non-leaf, two children. These are all leaves. And each leaf is on the same level, right? So it's full by the first definition. We know if it's full by the first, it's automatically full by the second. Is it complete? Well, each non-leaf has two children. That's true, except possibly on the lowest level, but for us, it's already the case that each non-leaf has two children, so we're good there. And on the lowest level, all leaf nodes are as far left as possible. Yep, the whole level is filled with leaf nodes, so we're good there. So this is full by both definitions and complete. So take a look at this one, and again, think about whether it is full based on both definitions and whether it is complete. So is this one full by the first definition? No, because it's not true that each non-leaf has two children. So this is a non-leaf with two children, this is a non-leaf with two children, but this is a non-leaf with only one child. So because of that, it doesn't meet this definition, meaning it's not full by the first one, doesn't meet that part of the definition, it doesn't also meet the second definition. So it's not full by either definition. Is it complete? Well, does each non-leaf have two children except possibly on the second lowest level? So anything above the second lowest level has to have two children. Yep, good to go there. On the second level, you can have two children, or you possibly could have less than two children. So two children, less than two children, but it's the second to lowest level, so that's allowed. Now on the lowest level, the leaf nodes all have to be as far left as possible. So boom, 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 yes. So it meets all the characteristics for complete. So this is an example of a tree that is not full by either definition, but is complete. Take a look at this one. So this tree is also not full because it has a non-leaf with only one child, that one right there. So because of that node, this tree is not full. This binary tree is not full by either definition. Is it complete? Well, no, it's not. So it does meet this first part. Each non-leaf has two children except possibly on the second lowest level. So again, this is the second lowest level. For each other non-leaf, this is a non-leaf, two children, so that's good. Okay, so it does meet this one. But on the second to lowest level, the leaves are supposed to be as far left as possible. Well, this is not far left as possible, right? It could go one more left, which is the tree we saw in the previous slide. So because of that, it does not meet that characteristic. So this tree is neither full nor complete. Take a look at that one. This tree is also neither full nor complete. So it's not full because, again, we have a non-leaf with one child. It also doesn't meet the second part of the definition for the first definition of full, each leaf being on the same level. So here's a leaf on this level and here's a leaf on a different level. So it doesn't meet that part either. For this, for complete, here the second level is this one. So for all the other levels, we want to have each non-leaf having two children, two children, two children, two children. So that part's actually good. But then again here on the lowest level, we want the leaf nodes to be as far left as possible. So this one would have to go all the way over here in order to make it complete. So because of that, this tree is not complete. Take a look here. This tree is not full by the first definition, but is full by the second definition and is complete. So by the first definition, does each non-leaf have two children? Yes, 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 yes. Okay, so that part is good. But by the second part, is each leaf on the same level? And that part does not meet that part because this is a leaf on this level and this is a leaf on that level. So it's not full by the first definition, but it is full by the second definition because each non-leaf has two children. So that less stringent definition, it is full. Is it complete? Well, does each non-leaf have two children except for possibly the second to lowest level? So this is the second to lowest level, the one we can ignore. All the others, we want to make sure two children, two children, two children. Yep, so we're good there. On the lowest level are the leaf nodes as far left as possible. Well, this is the lowest level. Could they be any more far left? No. So this is an example of a tree that is not full by the first definition, is full by the second definition, and is complete. Take a look at this one. So this is not full by either definition, but is complete. So does each non-leaf have two children? Well, no, that's not true because here's a non-leaf with one child. So because of that, it's not full by the first definition or by the second. It also doesn't even meet the second part of the first definition for full, that each leaf has to be on the same level. So it's not full using either definition. Is it complete? Well, again, for completeness, let's look at the second, ignore for a minute the second lowest level. Make sure all other non-leaves have two children. So two children, two children, two children, good there. And then look at your lowest level and make sure everything is as left as it can go. Is that the case? Are there any kind of missing spaces? No, so we meet that. So here's another example of a tree that is not full, but is complete. Take a look at that one. It's close to the one we just had. The difference is, you'll notice this guy's over there. That's the difference. So because of that one change, it is now not full and not complete. So it's not full for the same reasons as the previous one wasn't. We have a non-leaf with one child and also leaves on different levels, so it's not full by either definition. And here, it does meet the first part of being complete. Each non-leaf, if you ignore the second lowest level rather, each other non-leaf has two children. That part's okay. But on that lowest level, the leaf nodes are not as far left as possible because this one could be over there. That would be more to the left. So because of that, this is neither full nor complete. Take a look here. This is another one that is not full but is complete. So it's not full because we have an example of a non-leaf with one child. So that makes it not full by either definition. We also have another example of the second part of that for the second part of the first definition, leaves on different levels, so it doesn't meet that either. But for complete, it is complete. So again, we ignore the second to lowest level. Make sure all other non-leaves have 2 children. Good to go. Yep, yep, yep. And then on the lowest level are the leaf nodes as far left as possible. Could this node be any more to the left? It couldn't, so we're good to go. So this tree is complete. Again, small minor change makes this tree not complete. So it's not full for the same reasons. Here's a non-leaf with one child. Here are leaves on different levels. But now when we get to complete, so again, we're ignoring that second to lowest level, checking for 2 children on all other non-leaves. We have that part. But on the lowest level, are those leaf nodes as far left as possible? Well, no. This one could go over here, could be more to the left, so it doesn't meet that. So this is neither full nor complete. Take a look at this one. So this tree is not full by the first definition. So let's look at the first part. Does each non-leaf have 2 children? So 2 children, 2 children, 2 children, 2 children, 2 children. Yep, that part's okay. Is each of the leaves on the same level? Are each of the leaves on the same level? No. Here's a leaf on this level and here's a leaf on that level. So these leaves are on different levels. Doesn't meet that part. Not full by the first definition. But it is full by the second definition because each non-leaf has 2 children. So this is not full by the first one, full by the second one. Is it complete? Well, let's look at both parts. So let's look at, this is the second to lowest level. So we want to make sure every non-leaf, ignoring that level, has 2 children. So 2 children, 2 children, 2 children. Yep, good to go. But we also want to make sure that on the lowest level, the leaf nodes are as far left as possible. And is that the case? Well, this is the lowest level. This leaf node, there could be here, right? It could move to the left. So because of that, nope, it's not complete. So here's an example of a tree that is full by one definition, but not complete. Remember that if it's full by the first definition, it must be complete. But if it's full by the second, as we can see in this example, it's possible not to be complete. Take a look at this one. So this is neither full nor complete, and it's all from that root node. So here's an example of a non-leaf with one child. So that makes it not full by either definition. And because that non-leaf with one child happens above the second level, it also makes it not complete. So this is our second level. We can ignore any non-leaf nodes with one child on that level. But on any other level, if we find one with just one node, then it's not complete. So this is neither full nor complete. So there are some examples of full and complete. Again, I think, the definitions can kind of get a little confusing if you just sort of try to keep them in your head all at one time. I think the best way to do it is, like I've shown on the slides here, list out what you're looking for each characteristic and then say, okay, well, which is the second lowest level? What are my non-leaf nodes? And just go through and see if each one of your tree, if each node on that tree, meets what you're looking for, and thus does that characteristic apply. Couple final properties of binary trees. In any given binary tree, there are at most 2 raised to the power of h minus 1 nodes at any given level h. And this assumes that root is at level 1. So we had said that it's possible to think about the root as being level 0. This definition assumes that the root is level 1. So assuming your root is level 1, the most nodes you can have at any given level are 2 to the h minus 1. And in the entire tree, again using this 1 base height definition, so the root being at level 1, the most nodes you can have in total are 2 to the h. Notice just the h is raised there, minus 1, and the 1 is outside the exponent there. So this again assumes that 1 base definition, and a full tree using that first definition will have exactly this many nodes, 2 to the h minus 1. So here's an example. This is a full tree using the first definition, meaning it's also a full tree using the second definition, and meaning it's also complete. You can kind of think about that this is literally full, right? You couldn't add any other node into this tree unless you created a new level. So that's kind of how I like to think about that first definition of full. It's filled up. Unless you create a new level, there's no more room for nodes. So the most nodes you can have in this tree would be 7, right? Because the height is 3. So 2 to the third minus 1 is 8 minus 1 equals 7. So the most nodes you could have in this tree for a height of 3 is 7. 1, 2, 3, 4, 5, 6, 7. Yep. Look at any given level. So this is level 1. Most nodes you can have is 2 to the 1 minus 1, or 2 to the 0, which is 1. Look at level 2. The most nodes you can have is 2 to the 2 minus 1, or 2 to the first, which is 2. And then look at level 3. The most nodes you can have is 2 to the 3 minus 1, or 2 to the 2, which is 4. So a full tree will have exactly that number on each level and in total, but that's also a maximum. For any given tree, that's the most nodes that can be there. So there's some properties of binary trees. Let's now think about how we can use these trees, different ways to process them, to traverse the trees, to be able to use the data that we're storing in the trees.